Hello, Algebra 2 students. This is Mr. Kraft coming to you from my house. My apologies that the previous video came out with no audio. I'm not quite sure how that happened, but I think I've got it taken care of this time. What I want to talk to you about today is piecewise functions. Functions. Now, before I get into the math of it, since all you all guys are in physics, and we've discussed a topic in physics that actually gives you some explanation for how this works, I want to go back and talk about that first. So you remember when we talked about elasticity. So we said the example we used was a slinky, and we said you could stretch that slinky out. And we talked about the modulus of elasticity, which is simply put a measure of just how stretchy it is. Some things are not very stretchy. A piece of wood is not going to stretch. A slinky is going to stretch. Play-Doh's going to stretch. So we can stretch out and go back, stretch out and go back. Then we said you get to a certain point where you have the elastic limit. You pull the slinky out too far and it can no longer go back. It has undergone plastic deformation. And once that has happened, it is no longer capable of going back to its original state. So when you get to the elastic limit, it no longer gets longer or shorter. Then we talked about ultimate strength, which means how far can it go before it breaks. You pull the slinky to a certain point, and it just comes apart, it breaks. So you could say there are three different things that happen to the slinky. For lighter forces, it stretches out. For too strong a force, it stretches and becomes permanently lengthened out. And for a high enough force, it breaks. So if you were to graph the way the slinky is behaving, you drew a graph. Here's your x-axis, and there's your y-axis. Okay. So we could divide this graph like this. And you could say this first vertical line is the elastic limit. And you could say this here is the ultimate strength, where X is the force you use on it and Y is the length. So in this area here, maybe the slinky starts at a certain length. What the length is, it doesn't really matter. And as you smoothly increase the force, it gets longer and longer and longer and longer and longer until you reach the elastic limit. Once you reach the elastic limit, in this zone here, you've got plastic deformation. Back here, you could just say stretching. Once you hit plastic deformation, its length does not change because it can no longer resume its original shape and it won't stretch any further. So the way it was behaving over in the stretching zone and the way it's behaving in the plastic deformation zone are different. When you hit the ultimate strength, it breaks. So the length drops off immediately. Actually, it would probably be more accurate to just have it like that because it doesn't drop off, it just immediately breaks and ends up as a shorter piece. So in the, let's say, breaking zone, it does yet a third different thing. So elasticity is a common example that shows how the same thing can behave differently under different circumstances. If you wrote an equation to describe what's happening here, it would be different from the equation that describes what's happening here, which would be different again from the equation that describes what's happening here. That's what we mean by piecewise. One more very quick example, I'm not going to go into as an elaborate an idea. Another physics example. Some of you may be remembering this pleasantly, I hope, but you never know. Water, well, it starts off as ice. Ice has one specific heat. It does one thing when you heat it up. Then at the freezing point or melting point, 0 Celsius, it melts. And then you don't have ice anymore, you have water. Water has a different specific heat, so it behaves differently. Notice how the slope became steeper. Ice heats up faster, water takes longer. Then you've got vaporization, the boiling point, 100 degrees Celsius. I should have specified that too. And steam behaves differently yet again. So once more, the equation that would describe ice is not the same that would describe water, which in turn is not the same that would describe steam. Oh, and I guess I should have. So you have the ice zone, which is one thing, the water zone, which is another, and the steam zone, which is yet another. All right. Well, a piecewise function looks something like this. F of x equals, and you have a nice big curly brace. So those of you who have difficulties with curly braces, I'm not naming names, should practice on those again. So let's come up with some. Do that. So what this says is, with this particular function, it's saying that this function, if it's less than 3, if you're, well, actually, let me just go ahead rather than, because I think if you can see it while I discuss it, it will make more sense. So at 3, that's where you have the first break. And at 5 is where you have the second break. Just like we did with the elasticity, and also the same as we did with the freezing and boiling water. What this tells me is that from negative infinity, way out here, all the way up until you get to 3, it follows this rule. So you could say this is zone 1. Then between 3 and 5, it acts like that. You could say zone 2. Actually, I drew that wrong. Zone 2 is actually a Z2. And this I should have taken all the way over there. Okay. Then zone 3 is all the way from here out to positive infinity. So negative infinity up to here is my first break. That's where it does x plus 2. Between these two lines, it does 2x minus 4. And from this line all the way out, it is 3. So what I'm going to do, I'm going to graph them according to the rules for each section. For zone 1, I'm going to say x plus 2 in the first section. I'm changing colors. You'll see why. I'm going to make me a t-chart. And since this happens to be a linear equation in the format y equals mx plus b, where m is understood to be 1, and b is the y-intercept, x is 0, y is 2, and if x is 1, 1 times 1 is 1, 1 plus 2 is 3. 2 points are enough to get a line. So I'm going to have 0, 2, 1, 3. I'm going to connect the dots, literally. Best drawing in the world, but it'll be okay. I'm going to get up to here, but you see it says x is strictly less than 3. So that means when I get to 3, I have an open 0. It's just like when we did intervals with inequalities. Because at 3, I'm no longer following this rule. I'm following that rule. Because this says less than or equal, less than or equal. So now I'm in zone 2. So now I've got a different rule, 2x minus 4. And I'm going to make my t-chart for that. X is 0, y is negative 4, x is 1, 1 times 2 is 2, 2 plus negative 4 is negative 2. Well, this is kind of tricky. There's a couple of ways I could do this. You'll notice both these points are back over here. But that's no good because this green rule is not in effect over in the blue section here. So I could draw the line, then erase this part, or I could do this. I could say, well, maybe that's not the best way to go about doing it. I could say, let me put in 3. Let me put in 3. And then let me put in 5. Those are my boundaries. 3 times 2 is 6. 6 minus 4 is 2. 5 times 2 is 10. 10 minus 4 is 6. When I'm at 3, I have 1, 2. This is darkened in because the inequality sign is included. 5, 1, 2, 3, 4, 5, 6. That is included also. I connect my dots. And I did not write out how I was substituting that, but I trust you all see what's going on there. Last stage, I have fx equals 5. That's or 3, I'm sorry. I had 5 on the brain. Fx equals 3 when you're greater than 5. Well, as you may remember, when you have a linear equation in the format y equals 3, that is a horizontal line. Of course, fx is identical to y in this case. So 1, 2, 3, but I have to have an open circle again because this is not included. Horizontal out to positive infinity. So it starts from here, goes up, is not included, boom, jumps down, starts here, goes up like that, ends there, boom, jumps down to there, which is not included, and goes out horizontally. This is what a piecewise function looks like, and this is how you graph it. And seriously, no joke, I do recommend to my students that you literally get colored pencils. I know you're high school students, most of you are seniors, you're young adults, you know, but they colored pencils or little kids. But seriously, no joke at all. I do recommend on these that you get colored pencils and you literally graph these in different colors and work the equations in different colors, just like I did here. Because when you're first starting out with this kind of thing, it really makes it a lot clearer what you're doing. Of course, you can do it with regular pencils, what have you, but, why make life harder on yourself than it needs to be, especially during these days? If you don't have access to colored pencils, then I don't know, you might go out to Walmart and get some. I think that would be considered essential. Or if you just aren't into colored pencils, that's okay. But hopefully, this will clarify what the meaning of these things actually is. So, graph each part according to what its rule is. So the first part I graphed by the blue rule, second one by green, third one by red. Watch your signs and have the endpoints be open or closed as is appropriate. And hopefully, like I said, this looks kind of abstract. You look at something like this and like, gee whiz, what in the world does that even mean? Hopefully the examples from physics, and I'm actually glad that all of you are in physics, and I'm glad that we dealt with elasticity and changes of phase long before we got to this, because that really gives you some grounding for what this means. That is all for now, and I will talk to you later. Bye.